So let's continue about the MRI from last time. Thank you, Yumin, for explaining some of the concept which is relevant today. Some students ask advanced questions. Protons nucleus of a hydrogen atom is a proton, and that's what gives us a typical MRI contrast. So that proton is a small magnet, and it will align with the external magnetic field. So if we consider the proton as a small magnet, which you can consider positive charge, rotate from the top, it looks like counterclockwise, but if positive charge moves, you can have this magnetic field from the current, like a right-hand rule. So this is a net magnetic field, a small magnet. So in general, inside our body, all these protons are randomly oriented. However, if we align these, let's say, molecules inside our body, a big magnet from top and bottom, then the magnetic field will be in vertical direction. Then these tiny protons will align itself, mostly in parallel or anti-parallel direction. So this depicts the conceptual ways of how inside the body the proton will be aligned. So normally the magnetic field of individual protons will orient in random directions. Under a strong magnetic field, these magnetic fields of individual protons now align in the axis of the field, some parallel and others anti-parallel direction. So a net magnetic field vector here, it's shown is this arrow in the parallel direction, because a lot more will be parallel with having lower energy state. So now I want to discuss about how the principle of MRI, especially the concept of precession. You may or may not heard about precession, but think about a spinning top or a gyroscope. You may have seen, so you can see here, I brought this movie. So gyroscope is actually it's a spinning top, but it will, you see the top will not just drop, it will rotate. And that phenomenon we call precession. In Korean, it's called sechaunde. So the frequency of this spinning really depends on the strength of the external magnetic field. In this case, in this spinning top case, the frequency will depend on the Earth gravitation, like G. Okay, so in this case, it depends on external magnetic field. So that frequency of the spinning depends on the external magnetic field. This is very important concept because it provides us a way to reconstruct three-dimensional MRI imaging later on. So think about this magnetic field strength. When you went to the hospital, you will find typical clinical MRI is 1.5 Tesla. And recently, like some have like 3 Tesla, providing higher resolution. That's a clinical MRI. But there are also research MRIs exist, and they have a higher magnetic field strength, which such as 4.7. And I personally used to use a 9.4 Tesla for my research, and even 11 Tesla. And even now, I think I haven't written yet, 14 Teslas are available. Then you have heard the Earth has a magnetic field. So even the seasonal bird actually senses the Earth magnetic field to be able to move around the whole Earth. And that magnetic field is about 30 microtesla at the equator, and it actually is higher at the poles, and that's about 70 microtesla. Look at this microtesla and this. So our MRI machine is at least about like 100,000 times stronger than the Earth magnetic field strength. What about the refrigerator magnet? That's about 10 millitesla. So clinical MRI will be about 100 times at least stronger than this magnetic field. So when it comes with a charged particle is precessing, what's going to happen? So first, if you look at this, let me bring this diagram that for a charged particle to process, then you can see the large arrow shows the resultant external magnetic field. If you consider this as positive charge moving, charge moves is equivalent to current. When there's a wire-like current, there's a magnetic field forming around, and that you will realize. And small arrow here are particles' magnetic dipole moment, which is precessing. And here's a small diagram showing the external magnetic field look like. And with this, we will try to understand how MRI machine works. So I want to show the schematic of MR scanner and coils. How many of you have actually put yourself body into the MRI machine? And that's, you will remember that's going to be very loud, and also it takes like tens of minutes. So MR scanner looks, this is a little busy diagram, but for your own understanding and future reference, I put it here. So there's a scanner ball where a human gets in, and then there are also insulator, and there are coils. You can see it's a longitudinal section, and if body part specific receiver coils also here, for example, like brain MRI. So in fact, this chamber looks almost tube-like shape and surrounded by electrical coils, which I think I'm going to show you here. So you can see superconducting electromagnetic coils. So these are coils, okay? And also current will pass through the coils in clockwise rotation. And let me tell you what this means. So this is, let's say this view is from the foot to the head part. Then this clockwise rotation, if the current goes this way, then you will find out the magnetic field at the middle will be from here to into the paper. Or if it converts here, it actually, the magnetic field is from foot to head direction. Okay, so a magnetic field is produced longitudinal to the subject, as we showed before, in the direction of the feet, from the feet to the head. So what's going to happen for this? The person's a proton, a tiny magnetic dipole inside the body. So there's a main magnet here, and that surrounds this way, and then that will form a big static magnetic field from feet to head direction. And then you will have another coil here called RF coil. They will generate pulse to perturb these protons, and the perturbation returning, you will actually use the same RF coil to receive. So that you can see here. So because of this static magnetic field, you see this a lot of these small, tiny magnetic dipole moments aligned, and there's an external coil which is on the side, which will tune and matching the network, and you can see transmitter and receiver. So transmitter sends out RF, radio frequency signal, send it, then that will perturb these local magnetic dipole moments, and then the changes will come into a signal. So we use the same one, RF coil, as a like antenna to receive the MR signal. So again, if we look at this vector, so Z-axis is the longitudinal axis to the human, and then you send these external RF pulse to XY, a planar direction. So B0 versus B1, they are perpendicular. So that explains, there's already a question about T1 MRI, T2 MRI. You mean explained well. So the point is these are relaxation times, and that gives a different tissue contrast. So what do I mean by different tissue contrast? So first, we have to understand how these magnetization relaxation is occurring. So if you look at the Z direction, which is a longitudinal direction. So remember, the magnetic dipole moments are aligned initially. So when we gave a external pulse, then those will perturb and actually put this magnetic dipole to align on the planar direction like this. Okay, but this is brief pulse, and then it will be removed. So over time, these magnetic dipole moments start to come back and realign to the longitudinal because of a big static magnetic field throughout the body. So that is, if you look at the component of longitudinal z-axis, initially it becomes 0 because there's no component, and it starts to come back, and all these follow with exponential curve. Okay, so this returning recovery of longitudinal orientation time is called T1, and Yumin said like 37% and 67%, 63%, and these are all relevant to 1/E. Okay, so this recovery is along the static magnetic field, and this is good for contrast of soft tissue such as cerebral cortex, fatty tissue, and overall morphology. So T1 weighted MRIs made by this. And what about not just longitudinal, what about the transverse magnetization? So we look at that aspect. So initially it was aligned in longitudinal, and then you give the external radial pulse, that it will be on one axis. So let's say this one becomes this, and then this magnetization, and because of all this spin is a small magnetic field of this individual hydrogen nuclei or protons that will be spread out in this planar. So it will be spread out, and over time it will be almost like uniform. So it becomes a net direction, it will become 0. So if you look at this, initially it goes, so we are talking about this component, very high, but over time it's exponentially being decayed. So the rate of decay, we call it as a T2 relaxation time, and it means loss of transverse magnetization. So this is interaction of spin and transverse to the static magnetic field, how soon they will be diminished or disappearing is being measured. And T2 is very good for some pathology aspects. So edema, inflammation, and white matter region. So you can see this T1 and T2 are kind of an opposite direction. So in fact, you can model this as as exponential curve, and this relaxation time is defined as T1 and T2. And here's an example of actual images. So T1 weighted and T2 weighted. You can look at this. T2 is very good for showing up this ventricle, the liquid part. So edema, inflammation, and white matter. So T2 shows well for these, while T1 shows better soft tissue contrast. While you see the colors are looks like or flipped. So now I want to discuss it. This is a brief introduction. I think more advanced or deeper level, you have to read books or resort to other classes. But here I want to introduce you. MRI is really like programmable, which means it doesn't provide this image contrast by itself. There's many other ways of performing MRI scan, and there's a variety of information can be achieved, such as even not only structural but functional aspects. So here I want to discuss about diffusion MRI. So diffusion MRI is the here specifically we call DTI, or diffusion tensor imaging. So this is a most common ways of diffusion MRI, and which provides a connection inside in the nervous system, especially axonal fibers. So this is actually brain, and what we are interested in is think about this mechanism of a proton, which is a water molecule, right? So the movement of water in the free space will be uniform. However, think about axon. The axon fiber tract has a lot of myelination, and that myelination is very, very thin. If you look at with the view of a proton or hydrogen atom point of view or water molecule point of view, you are confined almost in two directions. So your diffusion will be limited to this longitudinal rather than across this myelin sheath membrane. So that provides an anisotropy. And if you analyze that, it actually provides the direction of axonal fiber. So that provides an exquisite shapes of this. And you can also color code and left, right with a red color and anterior, posterior, front and back as a green, and ups and downs direction, superior and inferior, you can mark it as a blue. So you can have this colorful map of fractional anisotropy, and this provides a connection system in the network of the brain. Of course, we have learned that there's the MRI technology which can be used for function. And this is a very important technique because non-invasively show the neural activity in fact, indirectly, because it actually is about hemodynamic change. But look at this an example, cortical activity during hand movement. So healthy subject using right hand, then this left part of motor cortex will show up, which is contralateral because right hand is linked to the left hemisphere here compared to the same side, which we call ipsilateral. So this one shows, and also this one also reveals some changes in stroke patients which got affected the region of hand. So you can see this changes in here. So this way, MRI, especially functional MRI, is also very, very useful, and that indirectly measure neural activity in the central nervous system. And the principle of functional MRI is in fact the changes in hemodynamics or blood flow change. And remember, the blood is composed of RBC and hemoglobin. Hemoglobin is actually containing iron atoms. So that is actually magnetic. So blood is magnetic, and we use that property to create a functional MRI. However, I have to say the contrast of functional MRI is very small. The difference between activity or non-activity is only a few %. So when you perform fMRI, it's not going to be just one time. It's going to be more like on, off, repeated multiple times so that the noise level is relatively canceled out while your signal will stand out so that you can create these images. Still, you can see a lot of noise aspect, but it's so powerful and precious technique. And that basis we call as a board signal. So you have to know this board because the mechanism or principle of fMRI is based on this blood oxygen level dependent. What do I mean by this? Is blood, especially oxyhemoglobin, and when the oxygen is released, deoxyhemoglobin has a differences in that magnetic property. So we use that part to create the contrast of MRI. So given the limited time, I want to give you the more resources for principle of MRI. Here are the links. Whenever you want to learn a little more, and you can actually go to this very nice website and YouTube movies. So to summarize this medical imaging, so this is an innovation in biomedical study, what the biomedical imaging technology has given, and it's keep increasing. So we can understand, we should understand the principles behind this imaging technology. Not only imaging, when you are using biomedical or instruments, better to really understand the basics, especially in imaging, this X-ray, CT, ultrasound, nuclear medicine such as SPECT and PET and MRI. So try to be familiarize yourself with this imaging modalities and their applications, and the basics of image acquisition and processing. Okay, thank you.